CH Lokesh. Today I will be taking about random variables in probability theory. Random variables are a fundamental concept that help us connect mathematics to real world uncertainty. In this presentation, I will cover the definitions, types, properties, and applications using clear examples. Introduction to probability and randomness. Before diving into random variables, let's remind ourselves about probability. Probability is the branch of mathematics that deals with uncertainty. Every time we do a random experiment like tossing a coin or rolling a dice, we cannot predict the exact outcome, but we can measure how likely each outcome is. Randomness is the foundation and random variables are how we quantify them. So what is random variable? A random variable is a rule that assigns uh, a number to the outcome of a random experiment. Or we can also say it, a random variable is a function that assigns a number to the outcome of a random experiment. So for example, if I flip a coin, we would assign 0 to tails and 1 to heads. And if I throw a dice, we would assign 0 to 1, getting 1, 1 to getting 2, 3 to get, and so on. 3 to getting 2, and so on. So this lets us use mathematics to analyze outcomes. Without random variables, probability would just be about odds like heads or tails, but with them, we can use numbers and formulas. Why do we need random variables? So we need random variables to represent uncertainty mathematically, and the random variables are used in data science, in AI, and finance. So because they let us represent uncertainty mathematically. For example, engineers use them to model machine failures. Financial analysts use them to estimate risk, and weather systems use them to predict rain or some any of this natural things. And AI systems use them to make predictions. Without random variables, all these fields would lack research tools to handle uncertainty. So when we hear any weather forecast, there's a 50% chance for rain and 30% chance for rain. And this is possible with the help of random variables. Types of random variables. So one is discrete random variable and another one is continuous random variable. So random variables come in two broad categories. So one is discrete and another one is continuous. Discrete variables deal with situations where the outcomes are countable. So for example, when we throw a coin, the outcome is getting heads or getting tails. So the outcomes are just two. These are countable. But continuous variables deals with measurements which can take infinitely many values, like height of the people in your classroom or temperature at a place and many things. Understanding this distinction is critical because the methods we use to calculate probabilities differ greatly for each type. So a discrete random variable can take only specific values. For example, when we roll dice, the result can be only 1, 2, 3, 4, 5, or 6. If I count the number of defective items in a batch, it might be 0, 1, 2, 3, but not 2.5. Discrete random variables are used a lot in counting based situations. And continuous random variables. Values over intervals, and we have discussed examples about height, weight. So think of measuring height again. Someone can be 170 centimeters, 170.5 or 170.55, and so on infinitely. Similarly, the time it takes to run a race is continuous. The values are uncountable. And instead of exact probabilities, we calculate probabilities over intervals. Key differences. The key difference between discrete and continuous random variables is that discrete outcomes are countable while continuous outcomes are uncountable. In discrete cases, we can assign probabilities to exact values. In continuous cases, the probability is the probability of an exact value is zero. Instead, we measure probabilities across ranges using areas under curves. The probability mass function or PMF is used for discrete random variables. It tells us the probability of each specific outcomes. For example, in a dice roll, probability of x is equal to 2 is 1/6. So PMFs must satisfy two rules. Probabilities are always between 0 and 1, and the sum of all probabilities equal to 1. Another one is probability density function, and the abbreviation should be small in small letters. For continuous random variables, we use probability density function or PDF. The PDF doesn't give probabilities of exact values, but describes how values are distributed. The probability that a variable lies between two numbers is the area under the curve between those 2 points. PDFs are essential in physics, biology, and economics. Probability mass function versus probability density function, and again, this should be in lowercase letters. PMF is probability mass function, and PDF is probability density function, and this PMF is probability at points, but PDF is probability across ranges. It's important. It's important to compare PMFs and PDFs. PMFs assign probabilities to specific points, like probability of x is equal to 3, but PDFs describe densities, and probabilities are obtained by integrating over intervals. In short, PMF is for discrete outcomes, PDF is for continuous outcomes. Cumulative distribution function, abbreviated as CDF, and it is also called as probability distribution function. Another important function is the cumulative distribution function or CDF. It gives the probability that a random variable is less than or equal to a certain value. For example, if x is the number on a dice, the probability that x less than or equal to 3 is 1/2. CDFs are always increasing and go from 0 to 1. So if we draw the graph for the values obtained from CDF or capital PDF, the graph should be increasing manner, since it is the cumulative sum of the probabilities. Expected value, and this is also called as mean. The expected value or mean is the long-run average outcome of a random variable. For a dice roll, the expected value is 3.5. Even though you will never actually roll a 3.5, for discrete cases, it's a weighted sum, and for continuous cases, it's an integral. Expectation is used heavily in statistics and economics. So, to find the mean, there are some separate formulas and other things. Variance and standard deviation. Variance tells us how spread out the values of a random variable are from the mean. If values cluster close to the mean, variance is small. If they spread far, the variance is large. Standard deviation is simply the square root of variance. Together, mean and variance summarize the central tendency of spread of a distribution. Common discrete distributions. Discrete distributions. Some common distributions include Bernoulli distribution, binomial distribution, and Poisson distribution. The Bernoulli distribution, which models a single yes or no outcome, like flipping a coin, and the binomial distributions models repeated independent trials, like tossing a coin multiple times. And the Poisson distribution models rare events in fixed intervals, like the number of emails received per hour. Common continuous distributions. We have seen about the discrete distributions. Now we are looking into continuous distributions. For continuous distributions, common examples include the uniform distribution function, and normal distribution, and exponential distribution. The uniform distribution where all outcomes are equally likely. the normal distribution or bell curve. It is also called as Gaussian distribution. Normal distribution is also called as Gaussian distribution, where which is incredibly common in natural and social phenomena. So we can see if we take the heights of every person in your classroom, you will get a bell-shaped curve. The the people with very short height are less, and the people with very tall height are less. But the people with average height are many in number. So the normal distribution is incredibly common in natural and social phenomena, and the exponential distribution, which is often used in model waiting times between events. Visualizing distributions. So visualizing distributions help us understand them better. The normal distribution looks like a symmetric bell. So we have discussed about the normal curve. This is nothing but a bell curve, and we call this as Gaussian distribution. The Gaussian curve is like a bell-shaped symmetrical bell curve. The Poisson distribution has spikes that describes as numbers increase. The uniform distribution is flat, meaning all outcomes are equally likely. Graphs provide intuition beyond formulas. Applications in science and engineering. Random variables are applied in science and engineering. Meteorologists use them to predict temperatures and rainfall. Quality control engineers use them to model defective products in a factory. Electrical engineers use them to model noise and signals. These applications show how math connects directly to the physical world. Applications in artificial intelligence and finance. So in AI and finance, random variables are everywhere. Machine learning algorithms use them to make predictions under uncertainty. Financial analysts use them to model stock price fluctuations. Risk analysts use them to estimate probabilities of rare but impactful events. Even daily life, like estimating waiting time for a bus, involves random variables. Conclusion and recap. Random variables connect math to reality. Two types. There are two types of discrete and continuous. The, the random variables are the foundation for statistics and data analysis. To conclude, random variables are the bridge between probability theory and the real world. They allow us to quantify uncertainty in precise way. We learn about discrete and continuous types, PMFs, PDFs, and CDFs, and saw examples of distributions and applications. Random variables form the foundation for advanced probability, statistics, and data analysis.